Welcome to The Explainer. So today we're going to look at computer networks through a completely different lens. I want you to completely stop thinking about boring cables and flashing lights for a second, and instead imagine a massive, sprawling, continental highway system. Think of the data packets as the cars, the routers as the major intersections, and today, well, you and I are going to learn how to be the ultimate digital city planners. We'll be exploring the inner workings of one of the absolute most powerful and widely used routing protocols in the world, OSPF. Okay, let's dive right into this. Here is our roadmap for today. We've got 1. The OSPF GPS system. 2. Building the master map. 3. Calculating OSPF route costs. And 4. Manipulating network traffic paths. Let's get to it.
Section 1. The OSPF GPS system.
To get started, I want you to imagine pulling out your smartphone to navigate rush hour traffic. You plug in a destination, and somehow it instantly knows exactly which roads are clogged, which ones are wide open, and the absolute fastest way to get you home. That exact concept is what brings us to OSPF, which stands for Open Shortest Path First. You see, OSPF is a link-state routing protocol. Honestly, it's best to think of it exactly like a modern crowdsourced GPS app, like Waze or Google Maps. Just like our phones constantly share real-time traffic updates with a central map, routers in an OSPF network independently share data about their connected links. They gather all this crowdsourced traffic data and then independently calculate the absolute best, most efficient route to every single possible destination in the network. And they do this using a brilliant piece of math called Dijkstra's algorithm, also known as the shortest path first algorithm.
Section 2. Building the master map.
Now that we know what OSPF fundamentally is, we kind of need to ask, how do these routers actually construct that giant highway map they use for all this navigation? Well, according to our source material, there are 3 primary steps to this major construction project. Step 1, the routers have to become neighbors. They basically introduce themselves to other routers connected to the exact same physical segment. Step 2, they exchange LSAs, which stands for Link State Advertisements. Now, I want you to think of these LSAs as hyperlocal traffic reports. A router creates an LSA that essentially yells out, hey, I have a connection over here, it's exactly this fast, and it goes to this specific network. They flood these traffic reports out to every single neighbor they know, who then passes them on to their neighbors. And then finally, step 3, once everybody has all the reports, they run that shortest path first algorithm we just mentioned to calculate the absolute best routes and lock them right into their routing tables.
And the crazy thing is the result of all that LSA flooding. Because every single router is passing those local traffic reports along until the entire network has seen them, it literally means that every single router builds the exact same master map. In official OSPF terminology, this identical map is called the Link State Database, or LSDB. Every router, R1, R2, R3, R4, they all have the exact same architectural blueprint of the entire network stored right there in their memory.
Section 3. Calculating OSPF route costs. Okay, so we have our map, we've got our traffic reports. But how does a router look at this master map and actually score the roads to pick the so-called best path? This brings us to a huge concept, OSPF cost. Now, think of cost as a toll that you have to pay to use a specific link on our digital highway. And here's the thing about routers. They are highly frugal. They will always try to pay the lowest possible total toll to reach their destination. The math to determine the toll on any given road is a super strict formula. You just take the reference bandwidth and divide it by the actual interface bandwidth. And the default reference bandwidth number that anchors all of our toll calculations? It is exactly 100. That stands for 100 megabits per second. This default number is hard-coded into OSPF from the old days, and it acts as the numerator for every single cost equation we do. And this brilliantly illustrates how the math actually works out in practice. Let's just look at this side by side. If a router has a fast Ethernet interface, which operates at a speed limit of 100 megabits per second, the math is just 100 divided by 100, right? So that results in an OSPF cost, or toll, of exactly 1. But check out the older standard Ethernet interface. It only operates at 10 megabits per second. 100 divided by 10 is 10. The slower road literally gets a toll of 10. So mathematically, the router is for sure going to prefer the faster road because the toll is significantly cheaper. But this legacy math introduces a really fascinating little quirk. What happens when you plug in modern gigabit Ethernet links, which run at 1,000 megabits per second? Well, 100 divided by 1,000 is 0.1. But here's the catch. OSPF costs cannot be fractions. They literally have to be whole integers. So it just rounds up to 1. This means that out of the box, by default, OSPF actually thinks a 100 megabit fast Ethernet link and a blazing fast 1000 megabit gigabit link have the exact same cost of one. It doesn't know the difference. And that is exactly why network administrators usually have to manually update that reference bandwidth number to account for modern, ultra-fast networks, keeping the math accurate for future upgrades.
So let's actually trace a route to see this entire process in action. Imagine router 1 wants to send a packet all the way down to the network on router 4. It has to add up the tolls of the outgoing or exit interfaces along the path. That's a key point, outgoing interfaces. So it exits out of R1, paying a toll of 100. It exits out of R2, paying another toll of 100, and finally it exits R4 down to the destination network, paying one last toll of 100. 100 plus 100 plus 100 gives us a total path cost of 300. And boom, that is exactly how OSPF calculates the shortest, cheapest route across the map.
Section 4. Manipulating network traffic paths. And this is where it gets really fun, because this is where we get to take control. You see, what happens when the mathematically shortest path isn't actually the path we want our sensitive or heavy data to take? Maybe there's a specific link we want to avoid. Well, this is where you officially put on your digital city planner hat. We don't have to just sit back and accept the default math. We can artificially alter these tolls to actively avoid congestion on default routes, or even intentionally force specific traffic down secondary backup paths. We can literally hack the scores to sculpt the flow of network traffic exactly the way we want it.
So you essentially have two primary ways to manipulate these routing scores on a Cisco router. Method 1 is changing the interface cost directly. You literally log into the interface and type IP OSPF cost 50. You are manually setting the toll, overriding everything else. The source notes actually highlight this as the recommended method. Now, method 2 is changing the interface bandwidth variable in the math equation itself using a command like bandwidth 1000. This forces OSPF's internal calculator to redo the toll based on the fake number you just provided.
So, the crucial point here is, actually scratch that, this is a massive warning from the source material that I absolutely have to emphasize. Using the bandwidth command is purely a mathematical trick for OSPF's brain. As the source clearly states, changing the interface bandwidth does not actually change the speed at which the interface operates. Let's be real, you cannot magically turn an old slow cable into a fiber optic line just by typing a bigger number into the software. There's no way. It strictly changes how OSPF calculates the toll, and absolutely nothing more. And wow, that brings us to the end of our journey today. We've seen how OSPF acts as this brilliant crowdsourced GPS system, building a master map and rigorously calculating the absolute cheapest tolls to move data across the globe. But far more importantly, you now know how to manipulate those very tools yourself. So my final challenge to you is this. If you were the architect of your own internet, fire up a lab, put on that city planner hat, and ask yourself, which network tolls would you adjust first to optimize your own digital highways? Thanks for joining me on this explainer, and keep building.